Hey everyone, welcome to the introduction and deep dive for SIG Instrumentation. My name is Pranshu. I've been working for 4 years with Red Hat, and I've been involved with the SIG for about 3 years now.
Hi everyone, I'm Richa. I'm a software engineer at Google, and I've been with the SIG for about 2 years. And that's it.
Hey everyone, I'm Damien. I'm working for Red Hat, and I've been a co-TL for SIG Instrumentation for 3 years now, I think.
Hi, I'm Yongrui. I'm also working for Google. I just recently became a new member for Kubernetes.
So on the agenda today are basically SIG Instrumentation fundamental atomics that we'll cover, as well as we have a dedicated session from one of our members towards the end of the presentation regarding how to contribute for newer contributors. So what do we do? The SIG Charter basically outlines the best practices for component owners in Kubernetes that encourages them to instrument their components using component base, which we maintain. And a big part of that are signals. So these consist of metrics, traces, logs, and events. There's also use cases, user stories, over the years that we received, for which the solutions didn't make sense for it to be just housed within the Kubernetes tree itself. And because of that, it led to the incubation of multiple sub-projects over time, which we'll talk about in a bit. But these sub-projects serve as valuable facets for the community to improve their overall customer cluster experience. How do we do it? We have these bi-weekly triage calls where we look at SIG Instrumentation assigned pull requests and issues and try to address them as soon as possible. We also look at KEPs every now and then and how they are doing in the enhancement repository. Because besides being just major feature-driven patches, these are very important to the SIG because they outline the SIG's stance on long-standing issues that may or may not be opinionated.
Thanks, Pranshu. I'll be talking about metrics in Kubernetes. So Kubernetes metrics follow the Prometheus metric format. This is the architecture for Prometheus. So all Kubernetes components are instrumented using Prometheus client libraries. All of these components expose their respective metrics in a HTTP/metrics endpoint. And any monitoring system that understands the Prometheus metric format can scrape these endpoints and store the data in a time series database, have monitoring on top of in the form of dashboards and alerts. This is one lesson that we try to reinforce every year, is that as benign as it may seem, but one should not just simply rename metrics, because this is a breaking change. Why this is a breaking change is because when you rename a metric, you're deleting the old metric and you're replacing that with a brand new one. So all of your existing monitoring, the alerts, the dashboards that were using the old metric, they would now stop working. This is a realization that came to us after numerous breakages that had happened for Kubernetes metrics in the past, which gave rise to the Kubernetes metrics framework. As a part of this effort, we wrapped the Prometheus client libraries implementation with our own implementations for metrics, and we added an annotation for the metrics to denote the stability level for them. The stability level is a way for us to express the likelihood of that metric changing in future. Also, with this framework, it allowed us to have some automation around these different stability levels, provided as a mechanism to centralize all the instrumentation-related code under a component base, a centralized place. So like I said, every metric in Kubernetes now will have one of these stability levels. Alpha being the least stable, has no stability guarantees, and a metric goes on from becoming an alpha metric towards a stable metric, which has the most stability guarantees. If you want to know more about the stability levels, the first link is where to go. And we also established an elaborate process for deprecating a metric so that you are not randomly breaking metrics users. And for that, you could visit the second link here. Next, I just want to call out a handful of some useful metrics that would be useful while you're trying to debug issues in your Kubernetes clusters. The first one is feature enablement metric. This is a beta metric which will expose all feature gates that are enabled at a given moment in time in a component. This is giving you also the information about which stage that particular feature gate is at, whether it's alpha, beta, or GA. We also have component health SLIs. These are exposed in a metrics SLIs endpoint. As you can see here, this endpoint is exposed by all Kubernetes control plane components and has these two metrics. These report essentially the results of the liveness and readiness checks that are done for each component. These are useful if you want to compute availability stats for the Kubernetes control plane components. And because these are telling you about the availability for these components, you could also use these metrics to measure the success rates for your Kubernetes upgrades, especially across minor version boundaries, because things are most likely to break there. These metrics are super low cardinality metrics and thus can be scraped at a high frequency, allowing you to have a more granular view of the availability for the control plane components. We also have metrics about our metrics. So we have the total number of registered metrics for each component, broken down by what stability level they are each at. If that metric was deprecated, we also record that in the deprecated version label. We have other metrics like total number of disabled metrics, number of hidden metrics for each component. And for all of these metrics, we have a nice auto-generated documentation that's available in the official Kubernetes docs repo, website. And this is a nice place for you to visit if you're trying to debug issues in your cluster and you want to quickly know what all metrics are available in the particular component you're trying to debug. This will give you information about what measurement each metric is recording and the schema for each of those metrics. That was all about metrics. Very recently, we have introduced a new way to debug Kubernetes. This is a separate set of HTTP endpoints that every Kubernetes component exposes, and we are calling these endpoints Z pages. These were introduced in 132, where we introduced two Z pages, status Z and flag Z. This was exposed by Kube API server at the time. Status Z gives you details about the component binary, things like when it was started, how long it has been up, what Go version it was based on, what is its binary version, emulation version, and can, of course, be evolved better to include more details as it grows. Flag Z gives you details about all the command line arguments that were used, along with their values, while starting the binary. And I'm happy to announce that both of these Z pages, status Z and flag Z, are now available in all control plane components starting 133, so they're not just limited to API server. You can find them for kubelet, scheduler, and the rest of them. Just ensure that you're enabling the component status Z and component flag Z feature gates while starting your binaries. One note about the usability for these endpoints is that they only support plain text format and are not a stable API yet. These are only meant for human readability, so they're not recommended to be parsed by machines. Their response schema is subject to change in future, but we are planning to make it more stable as the feature graduates to beta, so stay tuned for that. And we do have more ideas about introducing more Z pages for components. And if you have ideas about signals that can constitute a new Z page, then please do join our meetings. That was about Z pages, and I'll pass it over to Damien.
Yeah, so logs have been around forever, essentially in Kubernetes, and we use a custom logger in order to produce them, which is called klog, and it is a fork of the Google logger, which is specifically modified to support Kubernetes use cases. It has integration where we can easily convert Kubernetes objects to their string representation, for example, pods and nodes, and it makes it easier for developers to produce logline as a whole. It also conformed to the logger interface, which allowed us to extend the functionalities of the normal Google logger. But if you've been around in the Kubernetes ecosystem for quite a while, you might have seen that only the text format used to be supported, and there was no real structure in the log lines. It was always just a string-based log that didn't have any pattern that you could base yourself on. So that's what we are trying to invest in the past couple of years, which is to add a structure to this log to make it easier to query to make them easier to analyze and for essentially to make it to optimize the debugging time that you spend on Kubernetes. And to do that, we could have used, for example, the new slog logger that was introduced by Go one and a half year ago. But we introduced structured logging way before that, so we decided to stick with Klog and added support for structured logging in Klog. And this essentially today makes it easier for you to ingest the logs that are produced by your Kubernetes cluster into your logging platform. And also we support an optional JSON format that allows for easier use of logging query language such as Logl. So this was a huge improvement. And this is an example of what exists today. You can have the pattern at the top, and below is the example in the text format, which is what you would usually use in your Kubernetes cluster. And here's the example with JSON, and like it's way cleaner and easier to analyze compared to before what you used to do with grep and regex. Now you can use more advanced tools. But that wasn't enough. Like we noticed that it was hard to integrate the new structured logging across the Kubernetes code base, and we needed to simplify the way the data are passed down in the code tree. So we decided to introduce contextual logging, which essentially attach a context to the different call sites, and then we can set, for example, the pod name, attach it in the context, and we know that all log line below, like down the code tree, would set the pod name, and it will be consistent across all the logs that are produced by our components. And if you want to contribute to logging, like there is still a lot of improvement to be made. The feature is not GA yet. So you can contact Patrick Hawley or join the working group structured logging that meets bi-weekly. And it's definitely a good way to start your contribution journey. Now I'll talk about tracing, which is the newest addition, I guess, to the signals that we support in Kubernetes. If you are not too familiar with tracing, we essentially do distributed tracing in Kubernetes, which is, and it covers the gap where systems are becoming more and more difficult to understand for end users. There are multiple microservices involved, and it's hard to understand which one impacts your workload. In the case of Kubernetes, when your client sends a request to the API server, latency can occur at the API server level. It can occur from the storage, so etcd, and it's hard to figure out where it's coming from. But with tracing, it allows you to get like a tree-like overview of what's happening to a request. And below on that slide, you can see, for example, for an API server request, you would get a span for the time it's spent into the API server and the time it's spent in etcd, in the storage. So we introduced tracing in two places in the code, in two components, in the API server and kubelet. It became beta in 1.27. We wanted, and David Ashpool mentioned that GA was targeted for 1.33, but there was some delay, and we are now planning for 1.34. This is an example of how it looks like today. For the API server, you can see how much time is spent for a request in the API server in the different areas in the API server, because there is some serialization, there is some compute that is happening, and also the time in etcd. So now you can clearly see what's happening to your requests. The same goes for kubelets. If you ever try to optimize or debug the creation of a pod, you could see that there is a lot of interaction between kubelet and your container runtime, and a lot of things are happening. For example, you pull an image, you create the sandbox, and so on. So these are the steps that are recording in the traces and give you a better overview and makes it easier also to understand how these whole things works. But we've noticed that integrating tracing to our signals such as metrics and logging wasn't trivial and wasn't like instinctive, because the current debugging path and the whole debugging path that all Kubernetes user went through is usually that they would look at alerts or metrics, And then based on their finding in the alert and what is reported, they would search through the logs via different patterns. And tracing would just be like a side tool that will be used in some niche cases, but it wasn't part of like the debugging experience or like the general debugging experience. And what we want to do is to make it, to include it to the general debugging pipeline. So an end user could look at an alert and look at metrics. Based on these metrics, there would be attached exemplar, which are essentially a sample of a trace for one particular data point in your metrics. So, for example, you can see some dots on the graph, and that's the exemplar depending on your metrics, on how your metrics look like. And then from this exemplar, you can find the exact trace that is responsible for, let's say, 50 millisecond latency for your request. And then most of the tracing UI these days allows you to jump from a trace to a log as long as there is correlation between both. So you need to share the context between your traces and your logs, and then you can jump and get even more detail about what happened to that particular request. But this is still in progress. We've introduced exemplar to some API server metrics in 132, but it's not yet applied to all metrics in Kubernetes. And there is some additional work that we need to do in our library to make them easier to integrate for the developers of Kubernetes in general. And the span context in structured logging, David Ashpole mentioned also last KubeCon that we targeted 133, but we've noticed that there is some performance overhead that might need to be investigated. So this is still in progress. And now I will let Pranshu talk about the different sub-projects that we have.
Thanks, Damien. So going back to the sub-projects, I'll go over not all of them, but some of them that have had recent developments that are absolutely worth mentioning. I'll start with usage metrics collector. So for a while, we observed this gap in kubelet owing to Catvisor, where we weren't able to exactly have high fidelity metrics. And by that, I mean metrics with a granularity of less than 15 seconds. So we came up with this collector, which actually allows you to achieve per second high fidelity metrics. And in doing that, it allows you to have much more granular real-time dashboards and more reactive auto-scaling. Because you can use these metrics and plug them into your auto-scaling solution. It could be metric server, it could be Prometheus adapter, it could be Kata. On top of that, UMC does not export the metrics it operates on. And because of that, you save on your metrics backend storage, as well as you also save on compute, because the aggregation is performed at collection time. And because the aggregation is performed at collection time, you don't need to be dependent on PromQL. There's a straightforward configuration that you can configure and have your metrics straight away. I do want to give a very well-deserved shout out to Ilana Hashman, the previous co-chair, because she added cgroups version 2 support in UMC recently, and because of that, we are able to leverage features in modern distributions as well as container runtimes. And one example of that is now in UMC, we have much better, much more granular and insightful memory feedback as well as swap controls. It's all on the website, on the GitHub repository. The next sub-project I wanted to mention is probably the bread and butter of SIG. It's KSM, Kube-State Metrics, the most popular sub-project that we have, and it's the standard metrics generator for generating metrics for your native Kubernetes resources. You can see the list on your right, which are basically the supported resources as of now. If you want to add more, you're always free to send a PR. And it basically achieves this by monitoring API server and updates these metrics in real time. However, we did realize it was just a matter of time before users asked for metrics for custom resources. Why would we leave those out? Do we need to write a collector for our own custom resources? So for that, we came up with CRSM, which is custom resource state metrics. And you can see the configuration on your left here and the metric on the right. So you basically have collectors as configuration. You don't have to write your own collector. You can just configure, put it in the YAML file, and deploy that. Again, there were limitations to this. So what we observed down the line is how it, after a particular time that it evolved, when we tried to add a new behavior or a new field to the configuration, it kind of conflicted with the existing ones because the way this was written earlier was in a zero dependency, just down to arrays and hash maps manner. So that kind of prevented us from scaling and delivering, delivering this to the requirements, basically delivering on the requirements that the customers had in mind. And more importantly, anything that affected CRS would also potentially end up affecting KSM. So basically, because these were coupled together, if CRS goes down, KSM goes down. And that is bad because CRS metrics don't have stability guarantees, but KSM metrics do. So we need to basically fulfill those SLOs. And that's not the case when there's a bug in CRS. So, and of course, there was, the configuration itself was very involved after a point of time because it got evolved again and again, and all these behaviors were just being added to it. So enter resource state metrics. The KIP is up for that. Actually, we are very close to alpha graduation. And how RSM fixes this is basically it, first of all, decouples CRS from KSM. I should mention this explicitly that you can obviously have KSM running in your cluster as well as RSM and have them both operate at the same time to establish this complete metrics solution for resource schemata. It could be custom resources, it could be native resources. Whatever you need metrics from whenever you need it from the schemata of these, you can always have both of these deployed and you should be sorted. Also, the RSM configuration that I'll just show you in a bit is a superset of CRS configuration. So everything that you have in your CRS configuration, as it is right now, it could all be ported because we have conformance tests as of now, and these are 100% with 100% coverage. So the place, I would say the facet where RSM really shines is it introduces this concept of extensible resolvers. So you could, essentially, you don't need to learn a abstract DSL now. You can have your own, so whatever's hottest in the community right now, it could be cell, right? It's cell right now. And there's already a support for cell resolvers. So you see it emphasized on your left there. And so these are basically two metric families that are being generated right now. And the first one uses cell as its resolver. The other one uses no resolver. So it defaults to the unstructured API that's maintained by Segarch for more simpler cases, because that does not support arrays or hash maps as of now. But you can see that the label values and the values are now, you can write them in the resolver of your preference. If there's another expression language that comes into picture, you can always extend that and add that in RSM, and you should be good to go. However, even with that, the problem is that expression languages are Turing incomplete. So you cannot always have what you want. And there would be always this need to be unblocked, right? Or it could be that another resolver supports it, another language supports it, but you don't have the time to have that merged downstream, have that merged upstream, and then just wait for everything to happen, and then kind of use that. So for that, you can implement the collectors interface and use this as a library, and you should be able to define all your metrics in Golang itself. And that's the Turing complete way of doing that. So you will never be blocked. And that's basically what we wanted to get out of this. That was something that was not possible in CRS. And if this goes down, this has no stability guarantees, but your KSM metrics would still be in place. So yeah, that's RSM. And now I would like to give the mic to Yongrui.
Thanks. If you at this point still interested in SIG instrumentation, I will tell you a story about how I became a contributor to Kubernetes, starting from the instrumentation SIG. So how you can get started? So how I started is that at first you need to read through this documentation from the Kubernetes.dev. It has comprehensive information about how you can get started. And then you should be familiar with the role in the community. It's from members to reviewer, approver, and to the sub-project. And at this point, you can check the issues under the Kubernetes repo, and also check the issues for these sub-projects from the instrumentation SIG as well. And at this point, you can also attend the SIG meetings if you have any ideas to discuss, and also participate in the reviews and issues and docs. And you can also contact directly to the sub-project owners to share the idea within discuss and how you want to improve it. And for myself, I found the issue, basically it was something, has issue happen in a metric cardinality enforcement. So I discussed it in the SIG meeting and start with a simple PR to have a stopgap fix. And then I dig deeper to do the refactoring to improve the mechanism, and also cover it by the tests and integration tests and end-to-end tests, and also update the docs. And then I think at this time, it should be sufficient for me to apply for the membership. So I applied it and got a sponsor from other reviewers. And then I became a member. After that, my journey in Kubernetes communities still continue. So if you also want to explore, you can follow the link here. He has all the information about other SIG. You can also explore the other SIGs as well. But for my recommendation, I think it's for instrumentation SIG, it's better you start from here, because instrumentation SIG has a relatively easier bar and not have a very deep learning curve relatively. And so how you will, where to find us? We have 2 biweekly regular SIG meetings. Both happen on US Pacific time, 9:30 a.m. One is regular meeting and the other is strategy meetings where we'll triage for the issues and PRs. And you can also find us on the Slack channel, and we also have our mailing list. And I think our chairs and tech leads, Pranshu, Richa, and Damien and David, also welcome your directly contact them to share your ideas. We also added one more slide. If you want to become a member for underrepresented groups, you can also check out following the QR code here. I think that's it. So if you have any questions, you can ask now.